Hey everyone, welcome into this lecture on the natural exponential function. In the last lecture we talked about inverse functions, and in the lecture before that we talked about the natural log. So it now seems natural for us to define the natural exponential function as the inverse of the natural log, and that's exactly what it is. So here's our definition. We're going to give a couple different definitions here because this probably isn't the one that you're used to from, especially if you took AP Calc or Calc 1 in high school. But here's the deal. The natural exponential function, natural exponential function, which we're going to just call here y equals exp of x, this is the inverse of the natural log, which we again defined in a previous lecture here. So natural logarithm. And so recall here that the natural log was defined by an integral, right? So the natural log of x is defined to be the integral from 1 to x of 1 over t dt. And so we went over this in the last lecture, but it's important to remember now, especially if we're using this to define a new function. Remember that the domain of this function is from 0. You can go to 0, not including 0, but the y-axis becomes an asymptote, right? From 0 to positive infinity. And the graph passes through the point 1, because when x equals 1, this integral will be 0. And the graph looks something like this. As, like I said, a vertical asymptote this way, and it grows, but very slowly grows this way. Okay? Now, this is the log, the graph of the natural log of x. Now, if we want to define our natural exponential function as the inverse function to this, then this goes to the second lecture that we talked about. We have to reflect the graph over this line, right? Over this line y equals x. So there's our line y equals x, and then we know a couple of points that have to be on our line, right? So first of all, or our curve, I should say. This point right here is exactly the point where the height equals 1. So when x equals 0, y is 1. So that means that the exp of 0 equals 1, or the exponential function of 0 equals 1. And then all these other curves, so notice that let's do this part first, right? As we move to the left here, this curve, the red curve, the natural log, very quickly approaches, as a vertical asymptote, approaches the y-axis. Well, when we flip this all over, all these points are going to be moved up here to quickly approach but never touch the x-axis, right? And so the curve will look like this. And then in this direction we see kind of similar behavior, but it's like slowly moving away from this line y equals x. It's actually pretty quickly getting further away from the line y equals x because the curve is very slowly growing. So the further out we go, the further away it is from this line. And so the same kind of behavior is going to happen here, and this will grow actually pretty quickly. And so that's, again, the reflection of the curve for the natural log of x. It's the reflection over the line y equals x. And this is what we call the natural exponential function. So y equals exp of x right now, as of right now. That's how I'm writing this. And again, just based on the properties that we know, right? The domain, okay, I guess I'll keep writing in blue. It looks nice. So the domain of this function exp is all real numbers actually, right? Because the natural log takes on all real numbers as output values, so the exponential function will take them all as inputs. And it's hard to tell here because this looks like it's going straight up. It's not. It's growing very quickly, but as you move over in the x direction, there will always be graph above every x value that you pick. This just gets very high, right? Very, very big in the y direction very quickly. So the domain of this function is all real numbers. There's a couple of things we can say then, right? We have a horizontal asymptote here, and in the language of calculus, we can say then that the limit as x approaches minus infinity of our function exp of x has to be 0. So it squeezes down and approaches the x-axis, but only in that one direction, right? In the positive infinity direction, the function gets very, very large. So the limit as x approaches positive infinity of exp of x is equal to plus infinity. It grows very large very quickly. All right, and we said this, but I didn't write it down, right? The other property that we know for sure is that exp of 0 is equal to 1. So these are some properties of our natural exponential function. All right, well, you're probably wondering why am I writing it like exp, and the reason I'm writing it this way is because this is the way we've defined it, right? So far we've only defined it this way. So now what I'm going to do is go back and remind us of our old definition of the exponential function, and then just give us a couple of different ideas about. So I'm going to define a number, okay, in a couple different ways. So yeah, so it's alternate definition here. So alternate definition. This one, we're going to get into this definition more later on in the course, or very soon actually, but not in this lecture is the point. But very soon we're going to get into this definition in more detail. And this one says the following. So the natural exponential function. The natural exponential function y equals exp of x is the unique, that means the only one, non-zero function that satisfies this equation. So this is going to be called, I'm going to write down what it's called, but it's called a differential equation. And this is because there's a derivative involved here, but we'll write down what this means intuitively in a second. But it's going to solve the differential equation that dy by dx is equal to y at all values of x. All right, so what this means then, we can in some sense define the exponential function by its derivative, right? So this tells us then that the derivative with respect to x of our function exp of x is equal to exp of x. So the growth rate, remember the derivative is the instantaneous rate of growth, right? The growth rate is not just proportional to, but is exactly equal to the value of the function. And if we scroll back up to our picture, we see that as the function gets very small, its growth rate is small, right? Very, very small over here. That's why this levels out so much. So the growth rate becomes very close to zero when the function's value is close to zero. As we move along, the growth rate, the function increases, and it becomes steeper, right? It becomes steeper. As the growth rate, as the function gets bigger up here, the growth rate, the slope of the tangent line is steeper and steeper and steeper, and it approaches infinity. So as the values get much bigger, this thing is growing even more quickly, right? It's growing even more quickly. So there's another definition involving this differential equation here, and we will see this differential equation a lot moving forward, and we'll think about the exponential function in terms of the natural log was defined as an integral, right? In some sense, it's definite integral here. And the inverse function, then it should not be a surprise, can be defined by a differential equation. So by an equation that involves its derivative or says something important about its derivative. Now, there's more we can say about this, okay? It turns out that there's a number e, so this beginning of exponential. Also, this number e stands for the first letter in the name of Leonhard Euler. So Euler's number, sometimes also called the natural number. And we're not going to get too much into the details of this number, but I am going to define it a couple different ways. So the natural number, again, referred to as e. It turns out that there's an exponential function and the reason that this is called exp is because of the relationship here, right? But it turns out that y equals a to the x, where this a is a fixed number a. So for a fixed real non-negative constant that is also not equal to 1. A not equal to 1. All right, this function right here, y equals a to the x, which I'm sure you've studied in an algebra course, right? These functions, depending on what a is, their shape looks a lot like the shape of the graph that we just drew, right? It's this when a is bigger than 1, and it looks like this when a is less than 1. And when a is 1, it's just constant, so we just ignore that. This is an exponential function. So for all the different values of a that you could possibly pick, there's one value of a that obeys exactly this property. And in Calc 1, you should have proved this. Maybe we'll do it in this course, okay? So, but this equation, so y equals a to the power x, obeys or solves the differential equation y prime equals y for exactly 1. exactly one number a. And it turns out that that number is the natural number. So this number is either Euler's number, so it's the natural number e. And a lot of us probably know a way to estimate this number. So this number is irrational, which means that you can never write down the whole thing, but this number is about equal to 2.718, etc. There's a lot more digits there. Obviously, there's infinitely many, but it's about this number, right? So I don't want to say it wrong, but yeah. So the idea here then is that this number then, our function y equals exp of x can also be regarded as this exponential function e to the power x, right? And then the relationship with the natural log becomes more clear. And if you believe this, right? So now what do we have, right? So then y equals e to the x if and only if x is equal to the natural log of y. And so you can see this relationship where these two things kind of, you know, the x jumps down, the y goes over. It's a little bit easier over here. The base of the natural log is e to the x equals y. So this relationship, right, is the inverse relationship between the natural log over here and the exponential, natural exponential here. All right, well, there's a couple of different ways that we can write down what this number is. So in this video, I just want to give us a review of what the function is itself. But here's a couple of ways to realize the natural number e. So we'll call these definitions of the natural number. All right, and these say the following. Well, number one, e is equal to the limit as x approaches infinity of this, 1 plus 1 over x to the power x. So as x gets really big, the base here gets really close to 1, but the exponent gets very, very large, right? So you end up multiplying a number that's pretty close to 1, small, you know, small in the sense that it's close to 1, multiplying it by itself many, 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 many times, and eventually this curve, if you were to plot this curve, has a horizontal asymptote. It eventually levels off, and it levels off at this number e. And by the way, this, if you just take this and you let this just be like whole numbers or something, like n instead of x, then this represents the compound interest formula, or the growth, right? Compound growth formula. So this is like continuous compound growth. You get this number right here, e to the x, or is it, sorry, just you get the number e. E is the limit of this function right here. All right, another way to represent e is that e is equal to the sum, as n goes from 0 to infinity, of 1 over n factorial. So remember, n factorial says to multiply the number n by all of the integers smaller than it, down to 1. And there's one special case that we'll have to write down, but this is an infinite sum, right? It says 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial, 1 over 3 factorial plus 1 over 4 factorial, etc. 1 over 5 factorial. And goes on forever, right? And it includes all the factorials. Factorials grow very fast. So let's just write down these first few. Maybe let's write down 6 factorial as well, so you can see how quickly they grow. But 0 factorial we define to be 1. So that's just 1. 1 factorial is just 1. 2 factorial is 1 times 2. So this is 1 over 2. And at this point, now we've got a pattern here, right? So we just multiply the previous one by the next one. So 3 factorial is 3 times 2. So that's 6. 4 factorial is 4 times 6. So that's 24. 5 factorial is 5 times 24. So that is what? 120, right? And then 6 factorial is 6 times 120. So that's 720. All right, and then this continues on forever. And you can see that these terms are going to get very, very small, but they're going to continue to contribute a little bit at least. And you can even see from the beginning, the first 3 terms alone add up to 2.5. So you can see how, how quickly this thing shrinks if you believe that your number e is close to 2.718, right? Then 2.5, and then beyond, all the rest of it comes from beyond, right? If you go to the next one, you get 2.666666, right? So, etc. So that is pretty darn close just after those first 4 terms. So that's another way to represent the number e. And then just remember our exponential function then is y equals e to the x, and based on the definition, this must obey this property. E to the x prime is equal to e to the x. So it's a very, very nice function with this very, very desirable property that it's equal to its own derivative at every point. So I'm going to leave this here, and in the next video we'll do some examples of derivatives. I'll see you soon.